Do you know in GhostDAG data, you know what the role of blues anti-concizes is? Okay, so that's the basic trick of incremental GhostDAG. So if you have more time, I can teach you that fast. Yeah, so each of these blocks has a different, they all have this block as selected parent, but each of them can have a different merge set, etc., right? They can have a completely different merge set. So there can be like a block here internally. Now assume that there's like this blue block buried here, not necessarily even in the previous merge set. It can be like a few merge sets back. And this blue block is affected in various ways by each of these. So each of them, so A might have added a blue block from here, which is in the anticon of this E block. So the anticon of E is now increases by 1, but B, C, D might not have a blue block in their merge set, which is in the anticon of E. So they're not going to influence E's blue anticon size. Meaning each A, B, C, and D extend the blue set of their selected parent in a different way, which affects also the blue anticon sizes of previous blocks in different ways. So you want to maintain the blue set in a way which is incremental, meaning we want to hold each of A, B, C, D. We expect them to hold the diff information, how the blue set was mutated. So even though they all inherited the same blue set from their selected parent, they might mutate like some properties of the blue set, like the blue anticon size of past blocks. So the whole idea of blue set is so the way it works is that the blue set is actually never like, there's no single place where there's a blue set maintained, but essentially the blue set from a specific point of view is the incremental aggregation of all the pair block GhostDAG data on the selected chain of that blue set. The blue set is from a POV, from point of view of A, is essentially going to be the aggregation of all GhostDAG data along the selected chain from A. Like if you start from Genesis or from the pruning point and you apply GhostDAG data through the chain until you get to A, that's going to be like the blue set. And if you want to reconstruct the blue set in full, you'll have to do something like that. Like if you just need the blue blocks set, so you can go either up and down, just collect the blue blocks from each merge set, and that's the blue set, right? But if you need more information, like what are the anticon sizes of each blue set in order to be able to maintain following blocks, that's where it becomes more tricky. How do I know if block R here can be added as a blue block, even though it's in the anticon of E? So I must have tracked the amount of blue blocks in E's anticon already. And say maybe I know there's only 9, and K is 18, so I know I can add R. But I need to track this information somehow. I need to be able to know how many blocks are already in the blue anticon, because we don't allow more than K parallel blocks, so I need to know how much each block essentially has. And the amount of blue blocks each block has can mutate over time. It's not just a read-only. When it was added, it might have had like 8 parallel blocks, and then another block was added after it, increasing E's blue anticon set to 9, and then other blocks. So it can be it's a property that can evolve, and I kind of need to maintain it from each point of view coherently. So that's like the challenge of how to implement incremental GhostDAG. And that's the field I showed you. The blue anticon sizes is what we use. Essentially, it's saying it's a map from a hash to K, to K value, meaning a number. We use K type because it counts the amount of parallel blue blocks, which is bounded by K, so we can use K type. So it's a map from blue blocks to their blue anticon size. And it's not necessarily for the merged set blues. You can also point at the previous blue and say, okay, now this blue has more blue blocks in its anticon than my selected parent was thinking. Because from my merged set, I added more blue blocks which are in its anticon. So I'm updating that from my point of view, this blue block has now an updated number of parallel anticon blue blocks, so that anyone inheriting from me would know that, right, and would not pass the threshold of K. So whenever in the GhostDAG protocol, when I run and I have a blue candidate, right? So there's two properties I'm checking. I'm checking that my blue candidate doesn't increase the blue anticon size of a previously blue block beyond K. So if any of, so I'm looking at the set blue anticons of my blue candidate. And for each block in this set, I make sure that its blue anticon size is less than K, meaning that adding this new candidate will not surpass K, right? And I'm also making sure that the anticon itself is not, there's no more than K blocks, because otherwise this block would have too much, this new block would have too much blue blocks in its anticon. So I'm checking both directions. And once I take this blue candidate and I find that it has 5 blue blocks in its anticon, and I'm saying, okay, I can add it, then I have to go to each of these 5 blocks and update their anticon size from whatever it was before plus 1. And even though they're blue blocks that were colored by my parent, for instance, so I'm just saying, okay, from my point of view, they now have 6 blue blocks each in their anticon, or whatever they are according to plus 1 for each of them. So, and now if my child wants to inherit my coloring and extend it, in order to look up the blue anticon size of block E, it's not going to go to the parent which originally added E as a blue block, but it's actually going to go from the top down over the chain and search the entries of blue's anticon sizes. And the first entry you find, if you go top down, is the most updated one. So that's how it's used. It's not like, yeah, I'm relying on you to figure it out from what I'm saying. If we look at the code, so you have check blue candidate here for blue candidate. And I think essentially the logic is here. This means it's in my past. If we're here, P must be in the anticon of blue candidate, so we check for K limits. So we first look for P is like the previous blue block of my candidate, which is in the anticon of my candidate. So in order to compute the blue anticon size of it, you'll see we actually go over the chain. Yeah, we do what I described. We go over, in order to get the BAS of a peer, we go over the chain and search for the first appearance of here. If we find this in the map, so we return it. Because it's a blue block, we're guaranteed to eventually find it, because at the very least, it was when it was added, the parent who added it must have written down his initial blue anticon size. So we're always going to find something. So that's why it's just a panic here. Meaning this function is called when block is already known to be in the blue set. So it must appear at some point at the blue anticon sizes, and then the first one we find from the top is the one with the most updated info from our POV. So that's that check, and we check that it's. We also maintain the updated point of view. Whatever, I don't want to go in small nuances here, but essentially these are the checks. We're checking that the candidate itself, blue antiquon size, didn't go above K. And we also check that if the peer size is already K, we can also reject this block because adding it will make that previous blue have a K+1 antiquon. So this is that condition. So that's more or less the magic of incremental GhostDAG. I think it's simple. If you look at it, you'll see it's simple. But before discovering this algorithm, it wasn't even clear. When we looked at it, it was years back. So it wasn't obvious there's an efficient solution. Like we didn't know, obviously. Sounds like a challenge. How can you maintain a blue set with several point of views updating all the time efficiently?